Chapter 9, Newton's Big Book. Haley's question about with the competition trying to prove which way the planet, the path the planets take around the sun, rekindled or restarted basically Newton's interest in the way the planets moved. So he wrote a nine-page essay to answer Haley's question and then kept on going, saying, now that I'm upon this subject, I would gladly know the bottom of it. Basically, now that he had started the investigation, he wanted to get as far as he possibly could. So, in 18 months, he wrote arguably what could be considered his greatest masterpiece, his 500-page book titled in English, The Mathematical Principles of Natural Philosophy, but in Latin, we call it by its shorter version, which is just Principia. And this is a book that laid the foundation for modern physics. Even today, physicists or students who are studying the subject of physics generally refer to his book at some point in time. Now, when he wrote the book, his friend Haley was extremely excited. He was like, man, this stuff is awesome. You have to put this into print. In fact, you know what? Let me be your editor. I'll go through and correct it and make sure everything's good to go, and then I'll even pay to have the book printed. Now, immediately after the book was written, Robert Hooke, Newton's old enemy, immediately claimed that Newton had stolen some of his ideas and written them in his book. This made Newton so furious that he threatened not to publish the book at all. But thankfully, Haley was able to calm him down. Okay. Newton was really frustrated that once again, Hooke was claiming the right to something that he felt like was his own. He didn't feel like he had copied any of Robert Hooke's work and was so furious. He's like, fine, if Hooke is going to be that way, then I won't publish the book at all. And thankfully, Edmund Haley was able to convince him to do so anyway. The book finally came out in 1687 and caused a sensation. Readers loved it. And here's why. The readers felt like the universe had suddenly been explained to them. A French mathematician even said, does Mr. Newton eat, drink, and sleep like other men? Now, if we were to answer that question literally, we could say no, because obviously we know by now that he didn't take great care of himself. But that's not what the mathematician is asking. His statement is really more like, this book is so well written. Is this man even a human at all? Okay. In other words, is Mr. Newton a common man at all? It's almost like it's so well written and so smart that it's almost like he's not even one of us. Now, the book was very hard to follow. Again, Newton was quite the genius, so he wrote it very far above most people's intelligence level, but it still made Newton so famous that he was elected to Parliament, the reigning government in England at the time. Well, and even still today, it's part of their government. Now, he didn't really do a whole lot in Parliament. It didn't seem to be a big passion of his. He did, however, participate and vote in the favor of the Glorious Revolution of 1689 when they invited William of Orange and Mary to England in an attempt to scare James II, but didn't realize that when he got there, James II would have fled by then. So William of Orange just kind of marched in and sat down and took over. But anyways, he did vote in favor of that. But the only other time he actually spoke in a parliament meeting was to ask for a window to be closed. So he didn't take a completely active part in that much at all. Now, in his book, one of the main things that Newton included was his laws of motion. It's hard for us to understand how great of an impact Newton's book made on the minds of the people that read it, because today, even people who have never heard of Newton think of movement in the terms he invented. So, in our day and age, we are pretty used to the terms gravity, movement, motion, momentum, force, and things like that. But that's because for so long, all of society has been taught and is using Newton's foundation of physics and motion and gravity. But at the time, it was a completely new concept. So really, the people were pretty astounded, basically. It's kind of hard for us to understand how they felt because we've kind of grown up always knowing these things. So what information did this crazy awesome book contain? Well, first, he talked about the two forces that he studied, the one that pulled the apple towards the earth, and the one that made the planets orbit the sun. He also realized these were both the same force, and he gave them the same name. Now, in your notes packet, it actually says, let's see if I can get my pointer thing here. It actually says down here that Galileo was the speaker of this. You need to cross that out and write Isaac Newton because it was not him. It was obviously Isaac Newton. But what he said was, "It is now established that this force is gravity, and therefore we shall call it gravity from now on." Newton also created his three laws of motion. These laws explain the movement of everything in the universe. Now, when combined with a lot of mathematics, these laws can predict almost everything on the Earth, from tides to the movement of stars in distant galaxies. Now, we are going to look at the three laws of motion. I'm going to read to you the more detailed scientific version of it, and then I'm also going to read it to you in an easier to understand, explained way. So, Newton's first law of motion. Technically, it says what I have here in quotes. Every object will remain at rest or in uniform motion, meaning the same motion, in a straight line unless compelled to change its state by the action of an external force. This means that if something is moving, it will keep moving until something makes it stop. And then conversely, or inversely, not sure the right word there, but if something is sitting still, it won't move until some force makes it move. So let's take a marble, for example, which is why I have a picture of the marble up here. If we were to roll a marble across a gymnasium floor, that marble would roll for quite a long ways. Uh, but if we could expand the gymnasium floor to like, let's say about 10 times its size, we have a smooth marble rolling on a smooth wooden floor. Eventually, that marble will have to come to a stop. And that's because there are two forces acting on it. Number one, friction between the marble and the gym floor. There's not a lot of it, obviously, because they're both pretty smooth, but there is some. And eventually, that friction will cause the marble to slow down to a stop. The second force acting on it is also air resistance, which will cause the marble to slow down. But what Newton's law says is if we can remove all of the forces, okay, so if we could put these marbles in an environment where there is no gravity, there's no air pressure, there's no air friction, there's no air at all, and then we were to set the marbles in motion, then they would continue forever and ever and ever until something interfered and made it stop. Okay. I will also, in the slide after this in the pod, I'll include the YouTube video that I showed in class. It's a longer video, so you're only going to watch a small portion of it, but it does a great job explaining this law in pretty good detail. Now, Newton's second law of motion. Technically, it states what I have in quotes again. The velocity of an object changes when it is subject to an external force, and the force is equal to a change in momentum, mass times velocity, per change in time. So, very complicated way of basically saying this law shows how much force is needed to make something move or stop moving. Now, the equation is capital F, that capital F stands for force generally, equals m times A. So basically, force equals momentum times the change in time. So the best way to describe this is, let's pretend we're going to go to a playground and we're going to swing on the swing set. So it's you and a 400-pound man and a 10-pound baby went with you. Okay. Now you're going to be the one pushing on the swing set, and you'll have the 400-pound man in one swing and the 10-pound baby on the other swing. If we want to get both people to a momentum of, well, let's say about 10 swings per minute, which one will you have to apply more force to? Well, obviously, you'd have to apply more force to the 400-pound man. Okay. Now let's think about it this way. Maybe I want to push both people with the same amount of strength. So I want to apply the same amount of force. Okay. Who is going to have more momentum with that amount of force? The 10-pound baby or the 400-pound man? Well, because the 10-pound baby has less mass, he will obviously move further with the push than the 400-pound man and will therefore have more momentum. So that's kind of what Newton's second law explains. Now, the third law is actually quite common. You may have heard of this before, but this is the one that states that for every action or force in nature, there is an equal and opposite reaction. This means that every time you push on something, it pushes back just as strongly, but in the opposite direction. So, for example, if you have a balloon filled with air and you let go of the neck of the balloon, the air will rush out of the balloon, pushing the balloon backwards with the same amount of force as the air rushing out. Okay, so as the air is rushing out of the neck of the balloon is being propelled backwards. Okay, and the amount of force exerted on both sides is equal, but in opposite directions. Okay, another good example is walking. When you take a step, you pushing on the floor is what propels you forward. But as you push on the floor pushes back on your foot with the exact same amount of force. If it did not, when you push down on the floor, you would sink into the floor. Okay. You could also think about it if you were leaning up against a wall, right? If you're leaning up against a wall, kind of diagonally, and you're not in motion or anything like that, you are pushing on the wall with a certain amount of force, but the wall is pushing back on you with the same amount of force, just in the opposite direction. That's what allows you to not move. Now, if you're putting more force on the wall than the wall is putting on you, what would happen? Well, you would fall through the wall. Okay. So anyway, this happens quite frequently on a day-to-day basis. We just don't really think about it or know it because we're just so used to these things working in this way. Now, the only thing missing from Newton's explanation of gravity is that he never described what gravity actually is or what it's made out of. He only described how it works. Okay, so he never really said, gravity is made of this, this, this. Gravity is this. But he did describe that it is a force that causes this to happen or it impacts this in this way. But we can't really blame him for this fault because we still don't really know. We know that gravity is a force, we know how it interacts with us, we know how it affects us, but we can't really say what it's made of. So tomorrow we'll go through chapters 11 through 13. I do recommend, though, making sure you have everything highlighted in your packet um, for both Galileo and Isaac Newton so that you can begin studying for the test because that is going to be on Friday. Okay? Otherwise, let me know if you have any questions.